Up until this point, our main focus in this class has been real numbers and its properties, in particular the least upper bound axiom and its consequences. Among these is a notion of closeness and getting arbitrarily close to something, which we described formally in terms of sequences over the last chapter. In this chapter, we are going to be discussing functions between sets of real numbers. And as usual, whenever we have an important property and functions between things that have those properties, we're primarily interested in functions that do or do not preserve these properties. So in this case, the property in question is the notion of closeness. And so to talk about this rigorously, we are going to introduce a definition called a cluster point. So a cluster point, well, back up a little bit. We let S be a subset of R. Remember again from our previous classes that the functions we work on or care about may not necessarily have all of R as a domain or codomain, but generally speaking consist of real numbers. So we let S be a subset of R. C in R is a cluster point of S if our good friend shows up again for all epsilon greater than 0. If I take S, I get rid of C, and I intersect this with the open interval C minus infinity and C plus infinity, then that whole mess is not empty. Alright, so what I've written here is a bunch of symbols, and as we are wont to do, we want to take this and extract its meaning and some intuition about its meaning from it. So what does this mean to be a cluster point? Remember, epsilon is some small value, right? And what we're saying is, all right, if I have a point C on the real number line, and let's say S is a bunch of points here, a solid line here, a whole bunch of points here, solid here, 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 some more points, something like that, right? That means no matter what epsilon I pick, so let's let that be minus epsilon plus epsilon, no matter what epsilon pick, there's some stuff inside this interval other than C itself, right? There is some of S living inside the interval. And the important thing, as usual, is this for all epsilon noise, right? That means that no matter how far down I shoot my epsilon intervals in, no matter how far I zoom in, I'm always picking up something in this interval other than C itself. So again, think about this in terms of our primary focus of this course, which is closeness. It means that other than C itself, C is arbitrarily close to elements of S. No matter how tightly in I shrink epsilon in around this C, I'm always picking up stuff in S around it. So a non-example of this would be something like if I had the real numbers and I had S look something like this. So if I were to pick a C, say to be one of the elements of S, I'm going to call that C. I shrink in just a little bit and, well, there's nothing else in there besides C itself, right? But if I get rid of that C, then there is nothing else. I just have nothing, right? And so there's no clustering, hence the name, around that C. It's empty after you zoom in for a little while. And remember that if we look at this definition, that C doesn't have to be an element of S to be a cluster point of S. It just has to be an element of R. So, like, I could have chosen C maybe to be over here. But if I do that, I run into the same issue, don't I? If I go over there and I bring in a little epsilon ball, there's no elements of S in there either. So let's talk about some examples. What are the cluster points of some set? Let's say set number 1, R. This is sort of a silly example, but if I draw the real number line, any point C, any epsilon, there's always some real number in there, right? So yeah, if I have R, its cluster points are in fact R. Let's go ahead and take a look at the set Q, the rationals. And we think of the rationals as been sort of interspersed inside of R. If I pick any real or rational number, rational, irrational, any real number in C, we have a result from the beginning of this class, don't we? That if I take any epsilon ball around it, there's rationals inside there too, right? And if I zoom in and I zoom in and I zoom in, there's always rationals there. That's the density of the rationals. So the cluster points of the rationals are likewise also R. Let's next take a look at the open interval 0, 1. Like something like that. So we should note two things. One of them is if I pick a C inside this interval, any epsilon around that C, shrink it, I'm always going to pick up pieces of that interval, right? It's a non-empty subset of 0, 1, and since it itself is an interval, it has infinitely many elements, so I'm always going to grab something by doing this, right? So none of these are empty. If I pick a C out here, then yep, pick any epsilon sufficiently small and I'm going to pick up nothing. So this is a cluster point, this is not a cluster point. But what about right here at 0? Right here at 0, if I pick an epsilon ball, sure, on the left, I don't get anything. But on the right, I'm definitely going to pick up some values here, right? This epsilon interval will intersect some of my open interval. And if I zoom in and I zoom in and zoom in, these points over here are always going to pick up some of my my open interval 0, 1. The same thing happens if I pick that to my C. My little intervals will always pick up stuff to its left. And so putting these together, we can see that the cluster points of 0, 1, the open set interval, will be the closed interval 0, 1. Everything inside is a cluster point, because I can shrink in my epsilon small enough to grab them. And the endpoints are also cluster points, because they can pick things up on the outside. So maybe one last example to look at would be something like the set 1 over n such that n is a natural number. And so we have some sense of what that looks like. That's 1, 1/2, 1/3, 1/4, and so on and so on. Alright. So I think it should be pretty clear that if I pick things in between the elements of this set, I just take the two shortest distances, take the smaller distance, divided by 2, there's an epsilon interval, there's nothing in there, right? So we're good there. Even if I pick one of the elements of the set, let's say I pick 1, look at the closest one, pick an epsilon less than that, nothing in there. If I try to pick 1/3 to be a cluster point, take a look at these distances, pick something smaller, nothing in there. So nothing here is a cluster point. Clearly, nothing out here is a cluster point. So the only candidate of being a cluster point is 0 itself. If I put an epsilon bar around 0, this is minus epsilon, but who cares, there's nothing there. This, on the other hand, with the plus epsilon, don't we have 1 over n's that are always less than or closer to 0 compared to epsilon? That's just the Archimedean principle, right? And so putting all of this together, we get that the cluster points of this set that I've described here is just the set containing 0. 0 is the only cluster point of this particular set. So hopefully this helped illustrate what a cluster point is, what is or isn't a cluster point. We should see that there's some similarity to what we've talked about before in terms of closeness. Remember that prior to this, the way we described closeness was in terms of convergent sequences. So there must be a convergent sequence analog to this. Alright, see you in the next video.